All right, so it looks like we are ready and we have some people who are already here. Just a reminder that I do have subscriber only turned on for the chat. And that is just because in the past when I have done these chats, I have had spammers or whatever come in and kind of write inappropriate things in the chat box. Um, so and it should be approved for any school devices as well. So I went ahead and approved this YouTube channel. Please let me know that you can all hear me okay. I'm using a headset and I think I have all the audio worked out. So hopefully you can all hear me. Let's see. Again, hopefully you can all hear me. If you have questions, please make sure to put them in the chat box. Please reference any problems or anything like that. Um, and I will kind of answer them as they come in. So that is how you will want to be kind of putting things in there. Whoops, I accidentally closed that. Any questions that you have? Any problems that you need me to go over? See someone saying that the comments are turned off on my live. It should just be that you have to subscribe. Let me see what is happening. Give me 1 second. Let's see what I can do on my end. Oh, someone says it doesn't let you see comments if you're on your school account. So if it doesn't let you see comments if you're on the school account, so it looks like you can't even comment if you're on your school account. Because I do have my comments turned on. As I'm just going through. So it looks like we are coming up with a problem with people on their school accounts and not being able to stream, even though um, you should have the ability. Okay, so Max said he's on his personal account now, and you can comment. So it looks like a school thing, and I'm sorry, I did not know that it was a school thing related to the comments. Um, so it looks like you have to be on the school accounts to read or write comments. Wow, okay. I did not know that. So I am sorry for those of you who had to kind of switch around. I was not aware at all that you could not do that on your school account. So sorry for those of you who are on your school account. Hopefully you do have another account. If you still want to listen and have me solve a problem, you can send me a quick email. I do have my school email account up on another tab on another computer that I'm looking at as well. So if you want to send me a message through there, I will get to it as well. Um, so again, sorry for that for those of you who are watching. It looks like you need to be on a personal account, not a school account for that. Maybe that's something that I can talk to tech about to see if that's something that they can change. Not something I was aware of at all. So let's go ahead and get started. And again, if you have questions, go ahead and put them in the chat or send me a quick email at my school account. Again, that one is open. And I will be working through problems or going over topics that you want me to discuss. Reference either anything from your homework or from your study guide. Any questions? All right, so letter D on page 4 from the unit packet. June, do you mean the unit packet like the homework packet, or do you mean like the unit review packet? I am thinking you mean the homework packet. Okay, so again, so we're going to go ahead and do, this is on page 4 in our homework, and this is letter D. And this is a potential energy diagram. And in this problem, we are kind of given some sparse information. So for those of you following along, I will go ahead and kind of write that off to the side. So let's see. We are given in this problem, we are given the delta H of F of D, and D in this problem is our reactant, and it is a negative 50 kilojoules per mole. We are also given that our activation energy of the catalyst is equal to 35 kilojoules per mole. The activation energy, oops, excuse me, this should be my uncatalyzed. I always mix those up. So we'll say uncat, and then our catalyzed. The catalyzed is 10 kilojoules per mole. And we are given that the delta H of reaction is equal to a positive 5 kilojoules per mole. And so what we're asked is we're asked to find a bunch of other information, which we will go over, and to draw the potential energy diagram. So let's go ahead and start with just kind of outline our potential energy diagram. This goes from 100, and we'll go, let's say this is negative 100, and then we have negative 90, 80, 70, 60, 50, 40, 30, 20, negative 10. And then we'll go 0. So we'll go negative 30, negative 50, so you can kind of just see what my numbers are. Okay, so approaching this problem now that I have this information off to the side and I have my graph, the first thing I'm going to do is I'm going to go ahead and put a line where my delta H of formation for my product or for my reactant is. So my delta H for my reactant is right there at negative 50 kilojoules. The next thing that I could do is I know that my activation energy for my uncatalyzed is 35. So that means that it's 35 higher than my reactant. So that's going to be 10, 20, 35. Let's draw, I'm going to put like a little dot right there. And then my catalyst is 10. So just 10 higher. Going to go ahead and put a dot right there, 10 kilojoules higher. The other important information that we have is we have that our delta H of reaction of the forward is a positive 5 kilojoules. And what that means is that this is an endothermic reaction. And that means that my reactant or my product is actually going to be 5 kilojoules higher in energy. So it's actually going to be right here. And we are told that our product is called E. So if we draw the lines, we get a graph like this, and then we get our catalyst that looks like this. And so from this information, we can draw out a couple other important key information. We know that the delta H of formation for this is a negative 45 kilojoules per mole. We can say that our transition state right here, so our delta H of our transition state, that is going to be negative, let's see. Oh, this is on my catalyzed is going to be negative 40 kilojoules per mole. For my uncatalyzed, which is right here, my delta H of my formation is going to be a negative 15 kilojoules per mole. And then I could also talk about some information in the reverse. So in the reverse, what I want to identify is what my catalyzed and uncatalyzed is, my activation energy. So the difference between E, in this case, all the way up to my transition state. So if we think about my EA of the reverse, my catalyzed, that's going to be the difference. My catalyzed is the small distance right here, which is 5 kilojoules per mole. And then the difference between here and here, which is going to be my catalyzed or my uncatalyzed, excuse me, EA uncatalyzed. The difference between that one is going to be 30 kilojoules per mole. So we have those two amounts, and the only other thing that we can do from this problem or that we need to do is our delta H of reaction. Our delta H of reaction is always equal in magnitude but opposite in sign. So my delta H of reaction of the reverse is really just a negative 5 kilojoules per mole. So I think that addresses everything for problem D in the homework. Again, my suggestion is when you're given a problem like this is kind of fill in what you know and kind of worked backwards from that. We knew what our delta H of formation of D was. We knew our two activation energies, so I could put those. And then again, knowing that my delta H of reaction in the forward was 5, I knew where to put my product. So hopefully that was helpful. I did get an email. Can you go over the rate from graphs and find the average rate of disappearance of X from the unit review? Okay, let's look at a unit review problem. So if we are looking at our unit review, okay, so the rate from graphs in our unit review, this is going to be on the back side of the first page. And it is titled Rate from Graph. So let's look at that. I'm going to move this up and out of the way. And we are looking at our unit review. And I'm looking specifically at rates from graph. All right. We are given some important information before we even start looking at this. The fact that I'm given a graph of rate and the fact that I am given an equation 2x turns into y. I want to note that I can write out a kind of rate of reaction problem. And I could say that my rate of the reaction is going to be equal to negative 1/2 change in, whoops, let me actually undo that because that should have hard brackets around there. Change in the concentration of X over a change in time. And then that's going to be equal to a positive change in the concentration, whoops, of Y over a change in T. So when we look at this, if we are kind of paying attention to what I'm plugging in there, it's negative because this is being consumed. And then it's 1/2 because the coefficient is 2. And then this right here is my rate. So this is going to be the rate of disappearance of X. And then this right here is going to be my rate of appearance of Y. Now, if we look at this problem, we are asked to find the average rate of disappearance of X. And we're asked to find a couple different things from our graph. So we will use this in the second part. Someone said they are so confused. If you are confused, ask me a specific question about what you are confused about. Just saying you are so confused will not help me answer your question. So, when we are looking at problem number 1, or the first part, it says we want to know the average rate of disappearance of X, and we're going from 0 to 1 hour. If we are thinking about that time, we want to find the change in the concentration of X over the change in time. And we can get that from the graph. The change in the concentration of X, at the end of this time, we are at 17 molar, and we start off at 40 molar, so that's going to be the final minus initial. And then my change is going to be 1.0 hours minus 0 hours. So if we look at this, we can then calculate this out, and it is going to be negative 23 molar per hour. And then we can do the same thing for 1 through 2. Remember that our rate changes throughout the reaction, and the reason why our rate changes is that it starts to slow down. thinking about collision theory, if we have fewer reactants because they're getting consumed, we're not going to be able to produce products as quickly. So if we're going from, whoops, 2 hours, we can do the same equation. Max, I'm not using the 1/2 in this quite yet. So just so you know, that will come in another part. Right now, we can actually just calculate the rate just from the graph. Because the graph is specifically bringing that 1/2 in, because the graph is specifically graphing the rate of the disappearance of X. So we don't need to worry about that 1/2 because that's exactly what the graph is graphing. It's taking that into consideration. Okay. And this is going to be change in time. And for this one, we are going to have 10 molar minus 17 molar, and then again, 2.0 hours minus 1 hour, and that is going to be equal to a negative 7 molar per hour. So we can see that it's definitely slowing down. Now, that rate equation that we wrote up at top on top is actually going to come in now. We have this idea, we want to find the average rate of appearance of Y from 0 to 1 hour. Well, what we have in this first part right here is we know specifically in 0 to 1 hour, we know the delta, the change in the disappearance is negative 23 molar per hour. And so using our equation that we have at the top, we're going to choose those 2 points. So I'm going to use part of my rate equation to solve for the rate of appearance of Y. Negative 1/2 change in the concentration of X over the change in T, which is again from that equation that I wrote in white at the top, over the change in the concentration of Y over the change in time. And this is a variable that we're trying to solve for in this problem. So I could just plug in my negative 23 molar right there, and I'll get negative 1/2 times negative 23 molars per hour. And what I get is that it is going to be a positive 11.5 molar per hour, and that is for the appearance of Y. And that makes sense because Y is not going to appear as frequently as X because X has a higher coefficient, and you should also have a positive number. So that is that problem for that. Let's see, I have a couple other emails. I'm getting to them as they come in. Could you go over more rate laws on the homework packet? Any question? Okay, let's look at more rate laws. Okay. The more rate laws problem was a little tricky. Oh, how do we go about graphing it? When you graph it, what you want to do is you want to actually, so our original graph is something like this. You don't have to graph it precisely. When you are graphing it, what you want to do is we know that it's appearing, and we know that it's appearing slower than the product. So all you need to do is show your line, and you need to show it with a lower slope. That is all I would be looking for. So again, I would look to show that it's a positive slope because it's appearing, and I would be waiting to see that it is just a less steep slope than X because it doesn't have a coefficient. Okay, I am not sure who Shadow Destiny is, and I am about to kick you off because I don't know who you are, and you seem to be asking kind of off the wall questions. Um, okay, more rate laws. Let's look at more rate laws. And again, what I was saying about more rate laws, and this is on the last page of your unit review. When we're thinking about the more rate laws, this one is kind of tricky because to me it seems a little bit more theoretical because you're using this value x. And what you need to do in order to do this is you need to kind of use x in one of your variables. And I think that is really hard to kind of wrap your head around when you're solving these types of problems. So I will show you what I did to solve for this problem, but I want you to know that in any problem that you have on the test, they will be more aligned to what you have for rate of you. They'll be more aligned to the actual rate loss section. So you will be given a data table and stuff like that, just like we have seen on the homework. Okay, so in this problem, we are told a couple pieces of information. We are told that our rate is equal to K, concentration of NO, in its second order with respect to NO. And then we are told that we have a concentration of O2. There's no superscript there, so we assume that it's 1. And so it's first order with respect to oxygen. Now the problem does say what is the rate, and then they're giving us some different information. So for each of the bullets. But the important thing and kind of the problem where you need to kind of start using X as like a random variable is when it says when the concentration of NO is equal to 0.1 molar and the concentration of oxygen is equal to 0.1 molar, the rate of the reaction is X. And again, so what I did when I started to solve these is I realized that I need to somehow solve for K. So I said, okay, if I need to solve for K, I'm going to plug in my variables that I'm given in that first problem. I am told that my rate is equal to X. So we're just going to go ahead and put X. And it's K, and I am told that my concentration of NO is 0.10 molar, and that's squared. And my concentration of oxygen is 0.10 molar, and that's just raised to the first. And so I'm going to divide both sides by these. So I'm going to move this over. And I get this variable that says x over, and I'm going to give x units because this will be a little bit easier because our units for rate are molars over a second. And this is 1.0 times 10 to the negative 3, in this case, molar cubed. Now, if you remember anything about like exponents and rules with exponents, if you have a negative on the bottom, it is the same as having a positive on top. So really what K equals is 1.0 times 10 to the third, 1 over molar squared times a second. And again, whoops, and I forgot my X. We'll just add X in there. Hold on. X over 1 over molar squared times a second. And so it is weird to work with a variable like X in these problems. So when we do that, now that we have K, we can now plug it into our first one. So if we think about our first bullet, we want to know what the rate is. So we're trying to solve for the rate. So we want rate equals, okay, we have what K is, so I'm going to put 1.0 times 10 to the third x, 1 over a molar squared times a second. And then we're going to multiply that by my concentration of NO, which we are told is 0.20 molar, and that is squared, times the concentration of oxygen, which is 0.10 molar, and then that's raised to nothing. And then what we could do is, knowing this, we solve for this right here, and then we multiply it times 1 times 10 to the third, and what we get is that the rate is equal to 4.0x, and it's going to be molars per second. So again, solving that, keeping your x, looking at the units and solving those, we can actually get, in a way, what the rate is. It is 4 times what our original rate was, which also kind of makes sense when you think about it, because nitrogen monoxide is second order, which means that if the rate of nitrogen monoxide doubles, the rate should quadruple. And that's actually what's happening, is that my concentration of nitrogen monoxide does double. My concentration of oxygen stays the same. And so what we see is that indeed the rate of the reaction will be 4 times larger. All right, as I am continue going through, so someone asked, on the kinetic energy graphs, what does the shaded region on the graph mean? What does the line through the graph mean? An example on number 2. Okay, so yeah, let's look at some kinetic energy graphs really fast and talk a little bit about these, because these are helpful. Let me just pull that up really fast. Okay, so we looked at this idea of kinetic energy graphs. So here's this. So this is all about KE graphs. Right here is number of, you could think collision or particles. And here is kinetic energy. And we have a couple things on this graph. We might have a kind of a curve that goes like this. And again, what this means is that if you think of this curve, you have all these, anything under the curve, anything under this green curve is going to be a collision. And the collisions vary in the kinetic energy. So these molecules, or the collisions that happen kind of over here, are going to have really high kinetic energy. So these are going to have high kinetic energy. These are going to have very low kinetic energy. And the vast majority of the molecules are going to be right in between. When we look at the graph, we have this line. I'm going to grab a different color. We have this line for certain reactions. And this reaction, and this line right here, is called our threshold. And what that means is that this threshold line means that anything past this line will have what's called a successful collision. It will have a collision that produces a product, or a collision that will go forward. And so any molecules that collide with the correct orientation past this line will have a successful collision. Anything that collides with less energy will not produce a product. Now, we can also change things. So if we were to raise the temperature, we're still going to have the same number of collisions, but what we're going to see is that this curve kind of gets stretched out. And so what we see is that we're going to have more successful collisions because we have more area under the curve that passes that threshold. If we decrease the temperature, what we see is that the number of collisions that we have that pass that threshold actually lowers because the molecules have slowed down. The other thing that we could do with this graph is we could say, okay, if we add a catalyst, what we're doing is that we are lowering that threshold energy, or that activation energy. And so what we see is that more molecules will have enough energy when they collide to have a product being produced, or we can produce, or we can add an inhibitor, which actually increases that threshold energy. And so again, that shaded area after that line just shows where are the successful collisions. All right. Are there any other questions? I think I have covered the questions that have been emailed to me, and covered the couple that have come through the chat. Again, if you have logged on recently, um, unfortunately, through your school computer, it seems like you're not able to see the chat box. You are also not able to comment or anything like that. So I am taking people who are just kind of responding through email. So if you email me, I have that up. The other thing that I have on, because I have in the past had people kind of come onto the lives and type inappropriate things, is that you do have to subscribe to the channel in order to actually make a comment. But again, feel free to send me a quick email saying which problem you want solved or anything like that. So are there any other questions as we are kind of going through here? I have about 20 more minutes. Okay, so when writing thermochemical equations, how do we know if the heat should be placed as a reactant or a product? Okay, so thermochemical equations. So let's talk about that. So knowing what side the heat is going to be on. Now, it really depends on if it's endo or exo. If it's an endothermic reaction, that means that heat is being absorbed. And so what you're going to have is you're going to have X plus heat is going to produce Y. If it's an exothermic reaction, that means that heat is going to be a product. It's being produced instead of consumed. I think I might have said that wrong. Max, no, the graph does not have to be exact. I might not have scrolled down and seen your question before. And so what we see is it's going to be X is going to turn into Y, and it's also going to release heat. So what you want to think about is heat being released, or if it's being absorbed? Now, the one thing that you do need to know about heat, or kind of knowing endo and exothermic, is that you do need to know that combustion reactions are always exothermic. So if you see something along the lines of propane is being combusted, you need to know that that is talking about an exothermic reaction. So again, heat's going to be a product. Your unit packet also talks about things being melted or things like that. So remember we talked about this before. If we are turning something from let's say a solid to a liquid to a gas, these all require heat. So you have to input heat in to do this. So these are all endothermic reactions. If, however, you're going from a gas to a liquid to a solid, these are all going to release heat. So these are going to be exothermic reactions. And so you're going to be writing that heat as a product. All right. So June, hopefully June, let me know if that answers your question for that heat. And then I did have another question come through in an email having to do with reaction energy on the unit review. And this is going to be, actually, this is just going to be, we're going to say delta H of reactions. And these are our calculations. Now, on your test, you are not going to be given that whole table of formations, but every formation or every value that you need will be built into the problem. So you're not going to have to look through that whole sheet to find the substances that you need. They will all be built into that. So we have two methods. We have the product minus the reactant method. And this uses your delta H of formations. And the product minus reactant just means that when we're trying to find the delta H of the reaction, it is going to be the sum of all the products, and that's going to be the moles times the delta H of formations of all those products minus the sum of your reactants, and that's going to be the moles times the delta H of formation of your reactants. So you're going to be subtracting your products minus your reactants, and you're not going to change any of the signs. And I'll talk about that when we get to the bond energy method. So when we look at this, what we will see is we can figure out a couple of our values. Now I'm going to go ahead, just because I do not have this in front of me, I'm going to go ahead and write out the reaction that we're dealing with. We have C3H8 plus 5 oxygen gas plus 3 CO2 gas plus 4 H2O liquid. Okay, one of the things that you want to know is that when something is in its elemental state, like oxygen is right here, its delta H of formation is 0. And you could look that up on a chart. You would see that it would be 0. So if we're going to do, let's first start with all of our products. I'll go ahead and put my products in yellow so you can see that I'm kind of differentiating between those. So what I'm going to do is I'm going to take my products. I have 3, and this is, I'll put this in bigger brackets, carbon dioxide gas, which is negative 393 kilojoules per mole. And again, this value right here is coming from your table. Whoops, it's 393.5. Let me change that. And then we're going to add it to, so we're going to add all of our products together, and it's going to be 4 times, I have negative 286 kilojoules per mole. So those are all my reactants, and I'm going to add those all together, and then I'm going to subtract them from my, excuse me, I think I just call those my reactants. Those are all my products, and I'm going to subtract them from my reactants. And really, the only reactant that I have that's going to have a value is my C3H8, which is propane. And that is going to be a negative 104 kilojoules per mole. Be careful when you type this into your calculator. I would definitely do this stepwise, solve, say, this part, solve this part, add them together, because it's really easy with these to kind of misplace a negative or type it in slightly incorrect. Your delta H of reaction for this is going to be a negative 2.22 kilojoules per mole. Actually, I just did that, not 2.22. I have this as times 10 to the third kilojoules per mole. That makes way more sense. And so that is the delta H of reaction using our delta H of formations. Now the other part of this problem is our bond energy method. Our bond energy method uses this idea that when we have a chemical reaction, all the reactants, all the bonds of our reactants are being broken and they're being reformed to form our products. And so we take these averages, these are experimentally defined or experimentally obtained averages of how much energy it requires to break or make that bond. And so what we're what we're doing is that we're looking at those molecules and we're identifying what type of bonds make up those molecules. If they're reactants, we're going to say, oh, okay, those are going to be broken. So those are going to be positive because when bonds are broken, it requires energy. And then we're going to add it to all of the bonds that are present in our products. And we're going to say, okay, those are products, those bonds are being formed. And so those are all going to be negative. And then we're going to add those all together. Um, Going down really fast to the last part of that question, it says which of the two answers, or the two answers we will see will not match, which one is more accurate? I'm going to go ahead and say right now that the first method, the products minus reactants method, is more accurate because in the bond energy method, we are assuming that all the bonds are broken to form our products. And that is not always the case. The other thing that we are assuming is that the energy of each bond, even though they might be the same bond, are the same to make or break them. And that also is not always the case. So you need to, just kind of giving you some of that background information about which one is more accurate. Using our delta H of formations and using that method that we just did is more accurate. But let's go ahead and solve for our bond energy method. We still have to take into consideration our coefficients. But one of the things that we're going to see with our bond energy method is that oxygen is actually going to have a value in this one. So I'm not going to redraw all the structures because that's just going to take a little bit too much time, but I am going to identify kind of what bonds are in each structure. So if we look at our first structure, if we look at methane, we see that there are carbon-hydrogen bonds. And if we look at all those carbon-hydrogen bonds, we see that there are 8. Now, I'm going to leave this value as a positive because those bonds are being broken. If we look at the other part of this compound, which again is going to be positive, there are also 2 carbon-carbon bonds that make up that compound. So this is for my propane. Now let's move on. We also have another compound to break, and we have oxygen, and that is oxygen double bond oxygen. We do want to take into consideration that oxygen has a coefficient, so there are 5 moles of oxygen, and so there are 5 oxygen double bond oxygen bonds. And so those right there, these right here, are going to be all of my reactants, and my values are going to be positive. And then I'm going to add them to all of my products. And so when we look at this, I have, let's see, for carbon dioxide, there are 3 carbon dioxide molecules. But we also have 2 of the same bond, so really that's 6. These are going to be negative, so you can make this negative or you can make the value inside this be negative, and that is a carbon double bond oxygen. And then we have 4 moles of water, so again that's going to be 4 times 2 because there are 2 oxygen-hydrogen bonds within water. And again, that's going to end up being a -8. Again, I'm just making that negative since these are products. My values are going to be negative. So the last thing we're going to do is just plug in some information. So I'm going to do this kind of quickly because I think the main goal of kind of going over these problems is just kind of some of the theory or the ideas about them. Someone asked, why do we add the negative? We add the negative because those bonds are being formed, and so we need to show that energy is being released when we form those bonds. So we're making them negative. Those values are going to be the same, so we're just making them negative to show that the energy is being released. Okay. Again, and yes, Bryn, you are correct. The product reactant method is more accurate than the bond energy method. So if we do this, we're going to have, whoops, let's do, I changed my color. Hold on 1 second. We're going to do 8 times 413. I'm going to kind of leave off some units. I just want to do this quickly. 347. And we're going to add that to 5 times 495 plus, and this negative can go in front of the 6, or it can go in front of this number right here, 745. If energy was being absorbed, so if energy is being absorbed, what we're going to see, so Max, I'll answer your question in just a minute, actually. So we have this, and we have plus 8 times negative 467. And so if we add all those values together, we get our delta H of reaction to be a negative 1.73 times 10 to the third kilojoules per mole. So Max, what if the energy is being absorbed? So the energy is being absorbed when we're breaking bonds, which is why we have the reactants as being positive. Now, if you're thinking about the overall reaction, like when delta H of reaction is positive, what we're going to see is we're going to see these values be larger because it's going to take more energy to break those bonds. And these values right here are going to be smaller because less energy is going to be released. So what we're going to see is that if that's the case, this then will be positive, or it will be endothermic because it's going to take more energy to break the bonds than are going to be released when we create new bonds. But in this case, what we see with this answer, and this is going to be confusing, I just wrote that arrow to show endothermic. But in our problem right here, since it's negative, what that means is that we produced more energy forming the new bonds than we actually used breaking the original bonds. So it will work out in the end which ones will be negative and which ones will be positive. All right. Maybe about 5 more minutes if anyone else has any burning questions. When you are using the bond method, like we did here, the bond energy method, yes, always make the products negative and the reactants positive. Add them all together, you will get the right sign in front. However, if you are using the way with the delta H of formations, like we did with the first problem, the one that we did up here, you do not change the signs. These are 2 different methods that kind of require you to use 2 different processes. All right, I think we've hit a lot of the main topics. We have talked about kinetic energy diagrams. We've talked about rate of reaction. We've talked a little bit about rate laws. We've talked about product reactant bond energy. We've talked about some kinetic energy graphs. Bryn, yes, I believe I did. Bryn, I'm going to show you a picture up here, and this video will be posted at the end. Bryn, is this the type of graph that you're talking about, the one with the different lines? Okay, yeah, this video will be posted, so just go back and you will see that that addressed and I talk about kind of what's happening and stuff like that. So it is earlier in the stream. Any other questions? Your test does consist of about, I want to say, 15 multiple choice problems. You will see, not even, I can't even visualize the test right this second. You will definitely see a short problem with your potential energy diagrams. You will definitely see a rate law problem that you have to solve and a reaction mechanism that you will have to talk about, identifying your catalyst and intermediates. So make sure that you review your homework. And again, the answer key for the unit review is on Google Classroom. And I think if you guys have no other questions, we'll go ahead and wrap it up now. Double checking my email to make sure no other questions came through there. Nope. All right. Then I'm going to go ahead and log off. Again, this will be uploaded on Google Class, or not on Google Classroom. This will be uploaded to YouTube. I will put a link in Google Classroom when I'm done. I'm not sure how long it will take YouTube to process the video and post it, but it will be posted on YouTube when I stop it. So good luck with all your studying, and I will see you all tomorrow. I'm trying to figure out how to close it. I thought I would just close it and turn off my screen.